Hey pre-calculus kids, welcome to chapter 11, additional topics in algebra. In chapter 11, we will be discussing sequences and series. Only doing 3 sections in chapter 11, 11.1, 11.2, and 11.3. So let's start with 11.1, an introduction to sequences and series. In math, a sequence is just an ordered succession of numbers, and the key is ordered. So for example, we could have 1 half. What we do is we look for patterns. So let's suppose I had 1, then 1 half, and my next number was 1/3, and then 1/4, 1/5. Could you guess what the next term possibly would be? Hopefully you said 1/6 and would continue on like that. So the terms of the sequence, the very first one would be the first term. The second number would be the second term. This would be the 6th term, so forth and so on. Formally, a sequence is a function whose domain is the set of natural numbers. The natural numbers are 1, 2, 3, 4, so forth and so on. So from the above example, my inputs would just be the natural numbers, 1, 2, 3, 4, 5, 6, on and on and on. The output at 1 was 1. The output at 2 was 1/2. The output at 3 was 1/3, so forth and so on. Okay. Here, by observation, we can generate a template for this function. You notice that this function, f of n, we use n's instead of x's. You can use x's, but the n emphasizes that the domain isn't all real numbers this time. We're skipping everything in between the natural numbers. So at 1, we're at 1. At 2, we're at 1/2. At 3, we're at 1/3. At 4, we're at 1/4. So generically, the nth term is just 1/n. So what we just produced here is what we call an explicit formula. An explicit formula for a sequence gives you a template for any term in the sequence. So explicit formulas define each term of the sequence directly. These formulas allow us to calculate any term in the sequence without knowing the previous terms. So for this example, if I wanted to know the 100th term, I would know that it's 1/100, just based on the pattern. 1/n. So let's suppose I gave you the explicit formula n minus 1/n. So if my input is 1, my output is 0. My input is 2, I'm at 2, it'd be 1/2. 3, my input is 3, I'd be at 2/3. My input is 4, I would be at 3/4. Right, and I could go up, I could do the 9th element. I'm going to do the 99th, right? Even crazier. It's going to be 98/99. Right? So if we wrote this as a sequence, it would be 0, 1/2, we'd just write the outputs, 2/3, 3/4. The next one's going to be 4/5, 5/6, and then it continues on forever. So sequence notation, when we have a function that's a sequence, we tend to use sequence notation instead of the function notation. And we're going to replace f of n with a with a little subscript of n. So in this case, a sub n would be n minus 1 all over n. So for example, a sub 1 would be 0. A sub 4 would represent the 4th term in the sequence, which would be 3/4, right? And we could continue on forever and ever like that. Okay, often we use this notation. We use the curly bracket notation. And we generically put the sequence an inside the curly brackets. In this case, we know the template for this sequence, so we would actually put the template inside the curly brackets. And then for emphasis, sequences don't necessarily have to start at 1. They may start at 0. They may start at another natural number, but without loss of generality, if this one obviously couldn't start at 0 because then we would get a 0 in the denominator. But based on the situation, we are going to assume that we start at 1 and it goes on forever. So that would be how we would notate that this sequence's first value is 1, and then it's going to continue along our natural numbers, and it's going to go on forever. So let's look at another example. Let's suppose I gave you the template for the sequence. I said an is equal to -1 to the n power n squared. So I could also write this like this, -1 to the n, then n squared, right? So without loss of generality, if it doesn't specify where n starts and ends, we're going to assume it goes from 1 to infinity. So if we plug in 1 for n, it's going to be -1 to the n power, so the coefficient is going to be negative, and then 1 squared is 1. So it's -1. If n is 2, then the coefficient's +1 times 4, so it's going to be +4. The coefficient is, if n is 3, the coefficient's going to be -1. It's going to be 9. So notice this just alternates back and forth between integers squared. So 1 squared, 2 squared, 3 squared, the next number is going to be 16. And then we switch to -25. We go to +36. Here we go. No, we could stop at any point in time. We could do -1 to the n squared. We can start at 1, but maybe for some reason we only need to go up to 5. In that case, we call this a finite sequence. So this is an infinite sequence. And this would be a finite sequence. It's going to stop at the 5th term. So this finite sequence would be -1 is the first term, 4 is the second, -9 is the third, 16 is the fourth, and then we're going to stop at -25, and we would end there. Also note, for this sequence, this is an explicit formula. So it's an explicit formula, so I can pick any term of the sequence and I can write it without actually having to list it. So if I wanted to know what the 100th term of the sequence is, it'd be -1 to the 100th power times 100 squared. Right, so -1 to an even power is just going to be 1, and 100 squared is going to be 10,000. So I could tell you any term of the sequence. Not all sequences have explicit formulas, though. The next is an example of a very famous sequence. My guess is you've probably heard about it at some point in your mathematical career. It's called the Fibonacci sequence. Fibonacci sequence is defined only using the previous terms. So I'm going to list this guy as 1, 1. So it starts with 1 and 1. The next one is 2. The next term is 3. The next term is 5. Can you see what I'm doing here? Can you guess what the next term would be? If you said 8, you're correct. The next one is 13. 21. All right, so how do I get this sequence? Well, we start with 1 and 1, so these are going to be our first two terms. We're going to be told that it's 1 and 1. The third term is just the sum of the previous two. So 1 plus 1 is 2. The fourth term is the sum of the previous two. 1 plus 2 is 3. 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and it goes on forever. These numbers are really super cool. Fibonacci numbers occur lots of places in nature. If you've got a second, Google Fibonacci. And see how these numbers appear all around us. Okay. This is a recursive formula, though. If I wanted to know the 100th term of this sequence, I would actually have to list out the 99 before it. There is no formula. No one has discovered yet a formula that will give us the nth term of the sequence without actually going to that term. So the recursive formula for this is, it says that the nth term is just the term before it. So if we're at the 8th term, it would be the 7th term plus the 6th term. So this is saying that any given term is the sum of the previous terms before it. So this is the Fibonacci recursive formula. So if I wanted to know the 7th term, it would be the sum of the 6th and the 5th. So 1, 2, 3, 4, 5, 6, 7. So 13 is equal to 8 plus 5. If I wanted to know the 100th term, I would need to know the 99th and the 98th. But in order to know the 99th, I'd need to know the 98th and the 97th. In order to know the 98th and the 97th, I'd need to know the 96th. So I would actually have to list out all the terms to get up to that high of a value. So recursive formulas aren't as friendly, user-friendly as explicit formulas, but if you don't have one, you don't have one. All right, let's talk a little bit about a series. What's the difference between a sequence and a series? Well, a sequence is an ordered list of numbers. A sequence is an ordered list of numbers, but a series is the sum of the terms of the sequence. So if we have a sequence A1, A2, A3, then the corresponding series is A1 plus A2 plus A3 plus however many terms there are. So we write, instead of writing this all the time, this is the notation we typically use, A1 plus A2 plus A3 plus is equal to, we use this Greek letter called sigma. Sigma in math always means sum. Let me put a little side note here. So in math, when you see that Greek letter sigma, we're typically talking about a sum, and we generically put we put a subscript of I. We put down here where the first subscript starts, and then is it go on forever or does it stop? If it's an infinite series, we put infinity on top. If we have a finite sequence, it stops at some point, then the corresponding sum is called a finite series. So this would be an infinite series. If we have a finite sequence, then we get a finite sum. So we're going to add up all the terms, but we're going to stop at some point. We call it the nth term is where we stop. And the notation we use, we still use the sigma notation. We start at 1, we end at n. We use the generic subscript, meaning I starts at 1 and it ends at n. So the subscripts start at 1 and end at n. So let's look at 1 over 5. 1 over n, from n equals 1 to 5. So this, if n is 1, would be at 1. If n is 2, would be at 1/2. If n is 3, would be at 1/3, 1/4. Now we're only going up to 5. So this is a sequence, a finite sequence. Corresponding series would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. How we would write this using our sigma notation would start with, I'm going to do 1 over I generically. I is going to start at 1 and it's going to go up to 5. Now, just for note, if you add those values up on your calculator, you get 137 over 60. So that finite sum has a value. If we have an infinite sequence, the corresponding sum is called an infinite series. So A1 plus A2 plus A3 forever is going to be I equals 1 to infinity, A sub I. Now we could change this subscript. I could say K equals 1 to infinity, and then use the subscript K. So it's saying start here with the first subscript of 1 and keep going forever. I could do A sub n equals 1 to infinity. So as long as these match, we're good. We could do anything. I could do A sub p equals 1 to infinity. So this just means start your first subscript at 1 and don't ever stop. So if I had the infinite sequence, 1 1/2, 1/3, 1/4, forever. Right, so this would be this. That's my infinite sequence, and the corresponding sum would be 1 plus 1/2 plus 1/3 plus 1/4 forever. We would write 1 over, you can use whatever you want, 1 over n, I equals, nope, I'd have to start with n equals 1 to infinity. Let's look at this, what this means. Now, generically, typically, it's kind of a pain to put these in, so I'm going to, if you don't see it, it's assumed to be from 1 to infinity. So this means, actually, backpedal a minute, sorry. If you add these numbers up forever, you spend the rest of your life adding these up, the sum is going to be infinite. But let's take a look at this guy. If we took this, this says if n is 1, we're at 1/2. Plus if n is 2, we're at 1/4. If n is 3, 2 cubed is 1/8. Then it's going to be 1/16 forever. Note, if you sat here for the rest of your life and added these guys up, you would get 1. So this infinite series has a sum of infinity. It's unbounded, it keeps growing. This one's going to level out at 1. Isn't that kind of cool that we can add an infinite sum of numbers and get a finite response? All right, some properties of summation. We'll go more into that into a little bit later section. Properties of sums. If you have a constant, it's a finite series from 1 to n, that's just going to be, there's no, notice no subscripts here, so we don't have the sequence notation inside my summation. That just means c plus c plus c n times. Which is just going to be n times the constant. So if I said, find this sum, I equals 1 to, we will do 4 of 3. That just means 3 plus 3 plus 3 plus 3, which would be 12. But if I said 1 to infinity, we could have just done 3 times 4, but if I did this, this would be just keep adding 3 together forever. And if we kept adding 3, it would never be bounded. It would go to infinity. You have a constant in the same, every term has the same constant. We can pull the constant out. So if I have c times an, now notice, oh, I'm going to put here, I equals 1 to infinity. That's a constant. That doesn't change. This is what's going to change. The rule says we can pull the constant out, and then just look at this. So for example, if I said, what would, let's look at 3 times 1 over n, and n equals 1 to 5. Right, so that would be 3 over 1, and then it would be 3 over 2, 3 over 3, right, 3 over 4, 3 over 5. The corresponding series would go from 1 to 5, 3 times 1 over n would be 3 plus 3 halves plus 3 thirds plus 3 fourths plus 3 fifths. Okay, so we could add that up, or we could keep in mind that we can take the 3 out, that constant 3 out, and n equals 1 to 5 of 1 over n. But we already found this sum on a previous page. it was 137 over 60. So if we add this up on our calculator, we're going to get the same value as if we were to pull the 3 out, use this value that we already knew was 137 over 60 from a previous example, and 3 times 137 over 60 is 137 over 20. So if you have a constant in time inside a sequence and we're looking at the corresponding series, we can factor the constant out front and then just look at how that series behaves. Okay, just a couple more notes here. If we have a sum inside of a series, we can distribute the summation through the series. So we can just take the sum of the first and add it to the sum of the second. Likewise, if we have a difference inside of a series, we can take the sum of the first and subtract the sum of the second. So for example, if we wanted to do 3 plus 1 over n equals 1 to 5, we could just do 3, the series of 3 from 1 to 5, plus n equals 1 to 3 of 1 over n. And from the previous rules, we knew that this would be 15 because 3 plus 3 plus 3 5 times is 15. And we already know that this guy is 137 over 60. Right, so we add those two together, we get 15 plus 137 divided by 60. I'm going to always give exact numbers unless otherwise stated. It will be 1037 all over 60. And our last tidbit of information in this section is our factorial notation. So if you haven't seen factorials before, they are kind of cool. Factorial is, well, I'm going to give you the example first, then I'll write the generic template. If you see factorials are only defined for non-negative integers. So 5 factorial simply means 5 times 4 times 3 times 2 times 1. And if you multiply those out, it'd be 120. 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All right, and if you did that all out, it's 3,628. I'm sorry, 3,628,800. So by definition, n factorial is equal to n times n minus 1 times n minus 2. You go all the way down to 1. All right, so what's kind of cool too is you do have a factorial button on your 80 Ti calculators. If you go into, well, I'm going to do 10 factorial. So if I put the 10 in first, and I go 3 down, I hit the math button and go all the way over 4, knocks over to the PRB, and look at number 4 under PRB and hit enter. It's going to say 10 factorial on my calculator. Hit enter, and it's going to give me the 3,628,800. If I do 5 factorial, I hit math, go over to PRB, go down to number 4. 5 factorial is 120. All right, doing algebra with factorials can come in handy. Notice 10 factorial over 8 factorial was going to be 10 times 9 times 8 times 7 times 6. And I'm not even going to write them all down. 8 factorial is 8 times 7 times 6 times 5 all the way down. And notice the factors 8 down in the numerator cancel with the factors 8 down in the denominator. And it's going to be just 10 times 9, which is 90. So neat things, neat properties, and cool algebra things. Also note, 1 factorial is just 1, and that gets a little weird because the definition doesn't seem to necessarily support that. Right? 0 factorial actually has a value, and that's 1 also. This isn't a proof, but I'll just show you. Let's do 1 math factorial. My calculator is going to tell me it's 1, and then I'm going to do 0 math factorial. And it's going to give me the value of 1 also. So where does this 1 come from? I'll just give you an idea. Where do these, in this guy right here anyway. Let's see if we can kind of see why that would be the case, why they decided to call 0 factorial 1. All right, what is 6 factorial over 6? Well, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 all over 6, right? So you agree those cancel out, and it's just 5 times 4 times 3 times 2 times 1, which is 5 factorial. So what do you think 9 factorial over 9 is going to be? So 9 factorial over 9 is going to be 9 times 8 times 7 times 6 all the way down, all over 9. Then this time the 9s are going to cancel out. So the result is just equivalent to 8 factorial. All right, 100 factorial over 100. 99 factorial. Generically, z factorial over z is just going to be z minus 1 factorial, right? So let's let z equal 1. Well, if z is 1, plug in 1 everywhere we see z. Get 1 factorial over 1, which is equivalent to 1 minus 1 factorial. I just put 1 everywhere I see z because that seems to be the pattern. 1 factorial over 1 is 1. 1 minus 1 is 0 factorial. So we just showed that 0 factorial is 1. All right, have fun with this, guys. I will see you in 11.2.